Our lesson from last time was really, really long. And as I was making the video, I could tell that it was running kind of like it was taking a while to get through all that content. But there were just so many big, important pieces that we had to get used to with regards to significance testing. The good news is that this lesson should go a lot quicker, and we'll get to review some of those big ideas that we learned last time. I'll try my best not to make videos that long again, because that was kind of crazy. But there's a lot of good stuff in that video, and we're going to practice it as we get into this lesson right here. So we're going to practice what we already learned, and then I have one major new concept on type 1 and type 2 error that we're going to add on to what you already have been learning. So this first problem right here is a total review of what we did the last time. So I want you to pause the video and try this out for yourself. Read through the problem, figure out your parameter, define it, and then do your HOHA. I'm going to go ahead and talk through it now, so hopefully you have paused it and tried it yourself. But in this problem, it looks like Yvonne is looking at the percent of kids in her school who seldom or never argue with their friends. When you're setting up a significance test, you always test the parameter. And our big two are P and mu. You could do other things like we did a sigma last lesson with the golf clubs, but P and mu are the big two. Since they're talking about percentages right here, we are going to be testing P, which will be the true proportion of students at Yvonne's school who seldom or never argue with friends. And then we're going to establish our hypotheses for this problem. Remember that your HO, your null hypothesis, always has an equal sign in it. They say in this poll that it was 72% for everybody, and Yvonne is wondering if that's the case at her school. So her null hypothesis is going to be that the percent is the same as the supposed national average of 72%. Then for your alternative hypothesis, in your alternative, you are guided by the wording of the question or whatever the researcher thinks is going to happen. In this example, it doesn't give any sort of indication if she thinks it's going to be higher or she thinks it's going to be lower. We don't really know what kind of a difference she's expecting. She just cares whether or not this result holds true. So it could be lower, could be higher, we don't know. That makes this our first example of a two-sided test. If there's no indication in the problem that you have a gut feeling one way or the other, or you're trying to look at one specific thing, you do a not equal to alternative hypothesis. So this would be our setup for her little experiments. So then she conducts her study, and in her study, 96 out of 150 of the presumably randomly selected students say they rarely or never argue with friends. The first thing is 96 out of 150. As a decimal, I believe that's a 64%. Check that just real quick to make sure. So she does her little survey, and she gets 64% in her sample. If you remember from the last slide, our HO was that P equals 0.72. And then HA was that it's not a 0.72. Anytime you collect data, the first thing you do is you make sure that data actually is worth investigating further. If she would have taken her survey and gotten 72%, the same as HO, she'd look at that and be like, I guess there's no difference, and she'd be done. She wouldn't use fancy statistics. But because she got a 64% right here versus 72, we do statistical analysis to see 72 versus 64. Is that a big deal or is it not? So we're measuring how big of a deal that difference is. They do fancy math, which we still don't understand yet. And they got a p-value of 0.0291. They didn't ask for this, but I'm going to go ahead and at least talk through the interpretation of a p-value. Remember that what that means is assuming HO is true. So assuming her school is really a 0.72, just like the supposed national average. The probability of getting a 0.64 or more extreme So now I have to say more extreme in this one because it's not a greater than or less than. So getting a 0.64 or even crazier than a 0.64 has a probability of happening of about 2.9%. In other words, there's about a 2.9% chance of getting something as rare or as crazy as a 64%, assuming the answer is actually 72. Okay? Based on your comfort level or your significance level for a problem, you should say alphas right here, you would make a different decision depending on what your level of risk is set to be. Now, you always establish alpha before you collect your data. You decide what level of risk you're comfortable with before you start. Okay? So Yvonne goes into this problem and she's like, hey, I'm comfortable with a 5% level of risk. If something is rarer than a 5%, more rare than 5%, I'm convinced, I'm sold, I think HA is actually the way to go. So in this situation, they got a 2.9%. So because our p-value is only 2%, 0.0291, that is less than 0.05, which is our alpha, that means we're convinced. The evidence was strong enough to convince us. That means we are going to reject the null hypothesis that our school is no different. So we reject HO. There is convincing evidence for HA. And for this problem, convincing evidence for HA, so that the true proportion who never argue, never or seldom argue, is not a 0.72. In other words, I shorthanded my little context right here, but basically, there's convincing evidence that her school is not the same as what this poll said it would be. So at a 5% level of convincing evidence, we are convinced. Meanwhile, totally different person takes that same evidence, that same 64%, they see a 2.9%, and they say to themselves, gosh, 2.9% is too high for my taste. I'm not convinced by that same exact evidence. So write out a little conclusion based on using this significance level. I'll throw it up there. All right, so I wrote it up there with a slightly different spin on the convincing evidence statements, but to set up, you're going to fail to reject HO. You are never going to accept HO. So basically, different person takes the same evidence, that same 64 versus 72 that we talked about initially, but they're not quite impressed enough by that 64 to be convinced. They had very high standards. They needed under a 1% chance of that occurring by chance before they were sold. Okay? Either way, it's a pretty strong chance that her school is different, that her school is not 72. A 2.9% chance of happening isn't super common. It's just a matter of where you draw that line in the sand before you start your problem, how strong evidence needs to be before you're convinced. When you do these, you cannot change alpha after the fact. So let's say you go in saying, oh, I want alpha to be 0.05, but then you change it later. You can't do that. You set what will impress you beforehand, and then you base your conclusion on what you established. So hopefully that's all kind of making sense right there. That's our big concept from last time. We're going to add one new piece onto that, and that is the concept of type 1 and type 2 error. And I have a little story I'm going to tell you guys here to help you kind of wrap your head around that. So this past weekend, hypothetically, I was just really, really excited to have a little time off. I decided to celebrate by going to Dallas, Texas, little road trip here. And I was going to visit the Texas Instruments calculator facility. TI-84s, TI Inspires, all these great calculators. It's just my dream as a math teacher to go to the calculator factory. So I drive myself down there. Texas, I am just loving going around, checking out everything. It's just amazing. And then I go on my way, stop by the gift shop, and I'm driving out of town. So I'm heading back home after my amazing weekend trip to the Texas Instruments factory. On the way back, I get pulled over because apparently while I was there at the facility, at the Texas Instruments facility, a huge case of brand new cutting edge calculators went missing. So there was a huge case of calculators that was stolen while I was there in the facility. So they're checking my car and everything like that and talking to me, and they find a single calculator that was stolen from the gift shop. I happened to take a calculator from the gift shop on my way, and that was bad of me, but I did not steal all of the calculators in the facility. Meanwhile, Mr. Spinks was also there at the facility, also doing an independent road trip of his own. And he says he saw me stealing the case of calculators. They couldn't find the case of calculators on me. I say I didn't do it. Yes, I stole that one calculator, but I didn't steal them all. And that's the end of the evidence that was in the situation. All the cameras that were there weren't working at the time, et cetera, et cetera. The only things they have to go by are the fact that I stole that one little calculator and that one other person who says that I didn't. Okay? The idea of a significance test is going to play very, very strongly with the idea of going on trial and being a jury who has to make a verdict. The parallels between those situations come up a lot. Based on the story I just told, there are two verdicts that the jury could make. I'm going on trial and I'm going to be tried to see if I stole these calculators. There are two errors the jury could make regarding their verdicts. They could say that I'm guilty when I didn't do it. They could say I'm guilty when I didn't do it. They could also declare me not guilty when I did it. And then when you're looking at one of these problems here, like what would the jury decide in my problem? They had two pieces of evidence. I stole a single calculator, and then one other person said I did it. I would hope that in this country, I would not be convicted of stealing all of those calculators based on those two pieces of evidence. Yes, I stole one calculator, and yes, one person said what I did. But in this country, we have the motto or whatever, innocent until proven guilty. In other words, the evidence better be pretty strong. You better be pretty darn sure before you put an innocent person away. So I would hope under our country's philosophy, now sometimes that doesn't, like, the reality is that, like, yes, there are like issues with our justice system, et cetera, but the idea that our system is built upon is that declaring an innocent person guilty would be really bad. So an innocent person declared guilty would not be a good thing at all. Letting a guilty person go free would also be a bad thing, but you have to kind of weigh those two factors. How strong does the evidence need to be before you're convinced? If those two pieces of evidence were enough to lock somebody away, you would send a lot of innocent people to jail, or people who didn't commit that crime to jail. So that's kind of the idea when you're talking about significance testing in general. You have to weigh, if I make this decision, I might make this mistake. But if I make this decision, I might make this mistake instead. And in our trial example, there is hopefully a clear right answer for which one is worse. But if you're doing a problem about a golf club or something like that, it sort of depends on the problem, which of the two situations are worse. So what we need to do is define these two types of errors right here, and also talk about how we can mitigate or eliminate these errors as much as possible from occurring. One final thing about this slide, notice that when a jury requires or gives their verdict, they say guilty or not guilty. Not guilty meaning there's not enough evidence to declare that they're guilty. They don't come away either side and say, hey, this person's innocent. They didn't do it. He didn't steal the calculators. No jury is going to say that. They're either going to say, we have enough evidence to put you in jail for this, or we did not find enough evidence to convict. So that kind of analogy goes along with how we either reject HO, finding him guilty, or we fail to reject HO, finding not enough evidence to declare them guilty. So keep that trial analogy in your head as we're moving through this chapter. In the context of a trial, we have guilty and not guilty. With a significance test, though, we have something else. So I'm going to make a little 2x2 box right here. There are two things that we need to measure when we're looking at a significance test. HO is going on trial. HO is me who maybe didn't steal those calculators. And when we look at HO, either HO is going to be true or HO isn't true. So one thing we care about is the truth of HO. Is it true or is it not? Is Yvonne's school really a 72% or is it not? The other thing that matters when we're trying to decide if we made an error or not is what verdict we actually returned. So our verdict in a problem like this would either be that we reject HO or we fail to reject HO, found it not guilty. And let's run through each of these boxes here and talk about whether this is a good thing or not. So my first box says that HO is true. So the null hypothesis is true. I'm innocent, but we reject HO. We find it guilty. You found me guilty. This is a bad thing right here. This is an error. It is actually called a type 1 error. Usually you'll use Roman numerals for these, type I, type 1. So if HO is true and you reject it, you made the wrong call. That's not good, okay? Let's say HO is not true and you reject HO. So HO is guilty and you reject it, you declare it guilty. That's a good thing. You did good there. You made the correct decision. Okay? Now we're going to move down to this bottom row. If HO is true and you fail to reject HO is true and you did not convict him, that's a good thing. You made the right call right there. You didn't reject the innocent guy. Okay? So you didn't declare the innocent person guilty. And then the last box over here is when HO isn't true. HO isn't true and you fail to reject HO. That's also a bad thing. You made the wrong call on this one right here. Okay? HO should have been rejected, but you didn't reject it. That's called a type 2 error. Okay? I'm going to write down little definitions for these on the side right here, but I'll throw those up and then I'll talk about them. All right. So I've got the explanations written out for those two things that I just talked about. A type 1 error is when you find convincing evidence to reject HO. You reject HO, but you shouldn't have. So HO is true, you rejected it. That's kind of like in my courtroom analogy. That would be like saying a guilty person, or saying a person is guilty when they're actually innocent. That's what this box would be right here. Saying a guilty person, saying an innocent person is actually guilty. Okay? Then we have a type 2 error. And a type 2 error is not finding convincing evidence to reject HO when in fact HO should be rejected, or in other words, HO isn't true. So you would fail to reject HO when you should have rejected HO. In my courtroom example, we would say not guilty. We don't have enough evidence to say guilty when the person actually was guilty. So with type 1 and type 2 error in general, like when I do these problems, you heard me get twisted up on my wording a second ago. It's very easy to kind of make a silly mistake with those. You kind of have to be there in your head and be like, okay, it's this and this. Well, if they're innocent, but they're actually guilty, like you have to kind of go through your head like that and figure out what's going on. The book gives a really clever way to keep these two errors straight. The phrase that they use that I want you guys to remember is fail to, with the number 2, reject. So when you're keeping type 1 and type 2 error straight, fail to reject, 2 for type 2. So think about what that means. And again, that like little, like, okay, this thing in your head, fail to reject. That means I didn't reject, but I should have rejected because I made an error. So when I look at this problem, if I didn't reject, but I should have rejected, I didn't find convincing evidence when I should have rejected, okay, yeah, that's type 2. That means type 1 is the other one, where I did reject, but I shouldn't have. So you have to be able to keep those two things straight. And I think this little phrase is very helpful for doing that. Please know that with type 1 and type 2 error, they're called errors, but it's not because you screwed up. It's not, well, I mean, you made the wrong decision, but it's not because like you messed up your math or something like that. Type 1 and type 2 errors occur when you get that fluky, crazy sample that defies the odds. So like when we have a significance level of 1%, something has to be really rare before we find convincing evidence, before we're convinced. But there's going to be that occasional sample that just happens to be really fluky, and it's not your fault that that's what you got when you pulled the sample. In that Yvonne example, we were supposed to get 72%. We could, in theory, get like a 30% just by chance, just by random chance. And if we got that 30%, we would make a different conclusion than if we got like a 71% or something like that. So no matter what, when you have type 1 and type 2 error, you're looking at the fact that you could get a sample that just doesn't do what you expect it to do. Okay? It's not because you messed up on your math. So anytime in statistics you make a conclusion, there's a possibility that you're making one of these two errors. One of the things kids struggle with most with statistics is there's a lot more gray area than there is in a regular math class. In a regular math class, you got the answer right or you didn't. It's like cut and dry. Statistics has that gray area in it, and that's just part of the subject. In my courtroom example, it took I would probably be declared innocent in my calculator stealing example. Why don't we require like 10,000 witnesses every single time we want to convict somebody for a crime? Well, if we required that much certainty, we would never ever get anywhere. We would never convict anybody because our level of like what we need is just unrealistically high. If you convict somebody, you have to be pretty darn certain that they did that crime, but there's always that slight chance. People who are innocent get sent to jail, and that's a horrible thing. So there's a lot at play when you do these problems here, and that idea of gray area can make a difference. In a courtroom example, I would argue you need to be certain before you send somebody to jail. But if we're looking at like a medication or something like that, if we waited until we were 100% certain that medication makes a difference, nothing would ever happen with science. Nothing would ever happen. So that gray area is a big part of that in moving forward with things, even if you're not 100% certain. But knowing the errors that you might make is important in making that decision, knowing what you could be doing wrong. So anyway, that's my little speech on that. I have one last example to finish off our notes right here. You can go ahead and read this problem to yourself, but we're going to kind of talk about the whole process here with type 1, type 2 error. First thing I want you to do is read this problem, pause me, and do part A. State your null and alternative and define a parameter of interest. So I'll pause myself and I'll throw that up here. All right, so in this problem, we're looking at the average wait time in like the drive-through. And right now, that average is 110 seconds. They decide they're gonna bring in an extra employee. They're gonna hire somebody extra, and they're gonna hopefully try to reduce that mean. So the goal is to find evidence that the mean is actually gonna be lower than a 110, which is the old mean. Status quo goes in HO, always in equals. And then what the problem tells you. We want a smaller wait time, okay? Also, when you define your parameter, we're defining it for the new procedure. We already know what the mean used to be. So when you define your variable, make sure it's clear that it's for the new situation with the extra employee. So again, a little bit lower stakes than sending somebody to jail or testing like a life-threatening medication or something like that. It's just an employer who wants to know if they're using their money wisely. So if we think about what could happen, we have a type 1 error and we have a type 2 error in this problem that we could make depending on our conclusion. What would a type 1 error represent in this problem? Maybe pause me and see if you can think about what that would actually mean, and I'll talk about it right now. So type 1 error, remember, fail to reject. So fail to reject is a type 2, which means rejecting is a type 1 error. But if you're making an error, you rejected, but you shouldn't have rejected. So what would that look like in this problem? That would mean that it's finding convincing evidence that the mean, so we're finding convincing evidence for HA. We're finding convincing evidence that the mean wait time is less than 110. So we reject HO, we go with HA, but we shouldn't have. HO was actually true. So when the mean wait time is actually still 110. Okay, we reject HO. We found convincing evidence for HA when actually HO was true in the first place. So that is going to be a type 1 error. What would that mean for us in our restaurant? So I'm the restaurant manager. It's my restaurant. I end up making a type 1 error. Well, I basically paid an extra employee. I'm like, oh my gosh, this is working so great. I'm going to pay this person. And then it turns out I didn't even help the situation. So this would be me wasting money on an extra employee that didn't help. Talks about explaining the consequences of each one. So a type 1 error is what I wrote down in red right there. A consequence would be I just paid an extra employee, so I'm losing money as the person who owns the restaurant right here, and it didn't help my wait time. Okay? Try out a type 2 error, and same thing, pause the video so you can try it out yourself, but I'll go ahead and talk through it right here. Type 2 error is failing to reject. So if I fail to reject HO, that means I did not find convincing evidence for HA. So I did not find convincing evidence that the mean wait time is less than 110, when actually, so I didn't find convincing evidence for this, but I should have because it was true, when actually it is less than 110. So I failed to reject, oh, I didn't go with the new thing, HA right here, but I should have. So I didn't find convincing evidence the mean was less than 110 when it actually is. What does that mean for me in my restaurants? Well, the new employee that I tested out actually did help, but then I'd said, oh, no, it wasn't worth it. So a type 2 error in this problem basically results in a missed opportunity to improve the wait time. Okay, so frequently a type 1 error results in wasting money, and a type 2 error results in a missed opportunity, but that's not always the case. So you have to think through it in your head like I showed you right here. Which one is worse in a problem? It just depends. If my restaurant's doing really well, I'm making all kinds of money, and I just want to make sure I'm keeping people moving, keeping customers happy, I might be okay with making a type 1 error. I might have the extra money where I'm like, yeah, it's cool. I'm going to take that chance, and I'll go in a certain direction with how I set my significance level. But if I'm struggling to meet ends meet, I'm barely making any profit at all, my restaurant's in trouble, I probably can't afford to make a type 1 error. So I might err on the side of a type 2 error, which means I could be making my restaurant better, but I just don't have the money to take that risk. So in a problem, it really depends on what you kind of think and what your situation is.